Yeah, I'll look for that. That. Finally. Who's my other class reps? Michael. M-E. Cool. 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 Okay, great. I think I could start now. I think I should have everything ready. Chat, stream, and Zoom. And this will be silent. All right. Attendance sheet is passing around. Good afternoon, students. Good that you made it. Those who made it, those are in so this lecture is being conducted in hybrid. So you have those in Zoom right now. Those in Zoom, if you need to, you can put something on the chat, have the chat open. It might take a while to see it. I also have I think the audio is set up, so if you speak through the microphone, it's going to go through the speakers in the room, I hope. Actually, let me check it once. Yeah, so I could hear you. Whoever's speaking, I could hear you in the room as well, right? The only thing I don't have is a boundary microphone to pick up questions from the class to everywhere, right? So that's the only caveat. I'll just relay it on if I need to. All right, so the last thing, right? So most of you, or all of you, well, most would have done the partial assignment 1 stuff. So I'm hoping by the end of this week, I'll push out assignment 1, even though it's supposed to be done in week 3, but it's IPv6 related. So you'll have to use IPv6 lectures, which I already posted up. So you could take a look at that. And you could start your work from there and start working on the assignment. At least get the environment, looking at the environment, and then look at it, because it's going to be a template I'm giving you, and then you have to open that and then start to configure inside of it. So it's not to say that you start from scratch in GNS3. You're going to have a project you're going to import, right? I'll take my videos I did to showing you how to import those projects. So it's not going to be that difficult. It's going to be some work, yes. You can chat GPT all the way you want, but it's not going to help you configure and create your document, right? Because it's something based on your student ID number and stuff like that. You could try, ask it and see what it tells you. But then you'll have to tell you, create the commands to do it in this. And then you have to copy that command and execute it in the project and ChatGPT is not going to do that for you. You have to do it, right? If you do find a way to get one of those generative AI to actually interface with GNS3, great, let me know. I'll make some good money because that's an interface, interactive interface that your AI can actually manipulate on a third party of software. Right. So we're looking at basic routing. Now, you need to get this concept because we're going to use that concept in part of your assignment. What? Now, I am looking at IPv4 as your routing in terms of the layer 3 protocol. But in the assignment, it's going to be IPv6. You just have to understand that most cases IPv6 operate the same way in terms of routing as IPv4. There's some things with something called link local addresses. Personally, I mean, the standards to use link local addresses as your next hop, which you could see later on. But I would rather use the actual IPv6 address as your next hop. For me, personally, I think so because that kind of helps with your design. With link local, it's good, but it can be duplicated in all your configurations. So then you're going to have a lot of link local routes going out, and then it's could be problematic. If you use a dynamic routing with IPv6, which we may not use in this course, it'll be using link local for these things. So it give or take, depending on it is. But at least we got the concept for routing. We're going to do the IPv4 routing in the labs. Most likely either this Saturday or next. Most likely this Saturday. And then we'll look at the assignment. I may not do IPv6 routing in the labs. I'll check. I think one of the labs has IPv6 routing, so we can take a look at it. If there's anything, I'll just post it up. You can do it anyway. Right. So let me just skip through because I would have explained all of these. Those on the Zoom could get the shortcut to the YouTube link. Advantage of YouTube link is that you could rewind if you missed something and then play that back, right? Because I set it up with DVR. Zoom, you can't. It recorded, and you got to watch it until you finish, and then you can play it back. All right, so that's why I rather YouTube over the Zoom. Right, so I'll start from this. So I did a summary last week. Well, I think it was Monday. So today I did it already. So I'm just going back into more detail of what's happening here. So we're looking at the forwarding logic. You're sending packets to the default router. So this is the host forwarding logic. So I'm going to go into that depth because I want you to kind of understand when a packet goes from one device to another device. This is what it'll look at. Now, the CCNA courses that they have go into much more depth into depth. In fact, the CCNA is about 3 different courses, and each one is about 8 weeks plus or more. So that when it adds up, that's going to be about 8 by 3. That's 24 plus weeks. So that's like double LAN and WAN, basically, right? The LAN is about 12, 13 weeks, and WAN is so that's basically how it will end up. Wait. So they go into some more in depth. Right, so PC1 does some basic analysis and then chooses the send the IP back to the router, so the router forward back. Now, the basic analysis it's doing is going to take the IP address, the destination IP needs to go. So when you look at a ICMP packet, which we'll do later, it has a destination address. What it's going to do is it's going to take that and then look at do AND operation with its mask, and then it's going to compare that with the AND operation of its own IP with its mask and compare the two. And if it is the same in terms of the AND operation, that means it's on the same network. That's what it does, bitwise AND. So it converts the IP address into bits. And that's why it's in a nice dotted decimal format. You can easily convert that to bits, right? But the thing about it is that if it's not matching up, the only thing it could do, if it's not matching up, is to send that packet to the default gateway, right? We're going to more detailed metrics and stuff later on. But it sends to the default gateway. Most of you will know what a default gateway is, right? When you connect your computer into your home network, it automatically gets a default gateway via DHCP. DHCP is through your internet router, whatever router at home. Anybody setting up like advanced firewalls at home, things like IP, you setting up one? So you will play with default gateways and stuff, right? Remember, your firewall then has to use your internet router as a default gateway to forward that traffic through, right? So that's I forget the firewall name now. What's the firewall you use? The firewall you use. Sorry? OpenWRT on the router device. Okay, nothing nothing there. All right. I don't know why the name slips me, No, it's the Linux firewall. It slips me and I don't use it. So that's why all right, PFSense. Right. So those nobody using PFSense. Right. So I do hope that if you guys get it in Network Courier, please read up about it and try to set it up at home. All right. The good thing about software then and now, I mean, then is in my time, which is about 20 years ago, and now you can always download it. Most cases, download it, right? In this age, you could actually download it as well. Good thing, PFSense is free open source, so you can pull it down anywhere. But in my time, there was something called ISA, so you guys would not know about that, maybe, but it's actually based on as a Microsoft technology, Internet Acceleration, and I think it's Internet Security and Acceleration Server. We used to have this set up on campus, but because you could download the software wherever you want, I set up one at home, and I actually had an enterprise-grade firewall running. Interesting thing is once you set it up, it blocks everything, so then you have to allow internet traffic through it. It's really cool because where I was renting, I set up with a dial-up computer. Well, you guys don't know about dial-up, right? So I'll go through the story. I'll do it. I'll tell you why. Because what I'm doing, you can do that too now. Even then. So I say literally, I was saying out of the box, you can do that too. Nothing's stopping you from doing it. Right? So it doesn't matter, like I said, Network Courier going into, I suggest you start going to that area as well. Practice and try those things. Get the experience. So even though I'm not ISA certified, I have experience using it. Where I was renting, we had a dial-up computer set up. My ISA box was there. It connected with that dial-up modem to the internet line there. And I literally shared that between the apartment downstairs, which is about 3 rooms, apartment upstairs, and then I was in another apartment. So I ran a network cable across. So we had about 4 or 5 different rooms in that compound, and I was sharing dial-up internet there. So we had everybody using internet. That was like 2004 or 5 or something like that. I think I was doing my computer science master's at that time. But the thing is, I wanted to share the internet to other buildings and around the area, but I think there was a whole lot of other issues to deal with there. But the point was, it started off something small, and then you actually could grow it bigger and bigger and bigger. And I'm saying that was just something you practice on your own. So again, learning this is going to help you with setting that up to understand it. The one course will teach you about ACLs, which will kind of help with how you deal with firewall rules and all these things, right? But that's the one course. So anyhow, basic analysis, I digress, but I'm just giving you a background what you guys could do and follow up. And we have like less than an hour. All right. So it performs, once it realizes that the 2 IP addresses, bitwise matches, is not matching, it's going to send this packet to the default gateway or router in this case. Right? So it sends it to the router for the packet. Now, how would it know what is the router? Normally, it learns this router with your DHCP server, right? So when you connect the computer to your home network, it's going to pick up a DHCP IP lease. Inside that lease contains information about your router. It's going to keep that in that configuration. On your IP config/all, you're going to see that default gateway coming up, right? And DNS server and stuff. All that's sent through by your DHCP server. Now, you could set up one at home. You could use Linux to do it. I recommend Linux because it's easy to set up. Heck, I have Linux doing DHCP for the DCIT, computer science labs there. The labs, all that is the Linux DHCP server running right now. They want to move it to Windows. It was Windows. I moved it to Linux. They want to move it to Windows, but I'm not in charge of that network anymore. I'm in charge of South Campus. But anyhow, point is, I might have to do the same thing in South Campus. But so you see the knowledge I'm learning there. I can easily come, pack up my tool. If I had a network toolkit, I could say, put right. All that great part of your toolkit. Your knowledge is part of your toolkit too. So look at me. I'm not in this environment anymore, but I know how to set up a DHCP server. It could be Windows, Linux, or something like that. I don't know the exact steps. I could Google or ChatGPT to give me the steps. I document that, and I go down to wherever it is and say, oh, you need to get proper internet running here, or you don't have clients connected. Okay, I know how to set up that network, set up the DHCP, and then up and running fast. Right? So when we're doing configuration testing, one of the engineers was with me, and he did some diagnosing and realized why the wireless was not working was because of a DHCP server issue. And he told me, if he could leave it up and running. I said, no, leave it down because I have to fix problems first. And then that will come up, which is what I did. Fix that, and then it came up. So that's how it worked. But he realized the problem, and I realized the problem as well later on. But either way, I know to fix that. So it's going to get the IP address. Now, this thing, it has the IP address for the gateway. But the question is, how does that PC? So remember, we're looking at normally when you send a packet across, remember it is encapsulated in a frame. And that frame has MAC addresses in there. So the question is, how does your PC know about the destination MAC address, which is your router MAC address in this situation? Right? So how it knows it, it'll have to do basically the app. And it's going to send an app broadcast. Okay, who owns this? How it knows the IP? It knows it from the DHCP server. Who owns this IP? Right? Tell me, and it'll give me the MAC address. So it just sends that onto if it's a direct connection wire, like in this case, let me go to the mouse here. If it's just this direct connection here to here, it'll just be a broadcast to the router interface, and that's it. It'll just respond, and it'll get back the MAC address, and then it'll just encapsulate and send that packet to that router. Right? So what's happening here is not on the same LAN as PC1, which I just explained. Knows where to a nearby router, the same LAN called the PC1 default router, which we have done. Now, there are cases where you can actually use you can have more than one router on the same network with the PC1, but you have something called a metric you add on, so that if it's a all the default traffic goes on through that router. But any specific networks, you set up what you call a route, you modify the routing table and add a route to say, okay, this traffic goes through another router. And you can play with that, but then you have to be very customizable, and it is not automatic anymore. But it helps with if you want to balance traffic. Nice way if you have like 2 internet lines coming in and you want to say, well, flow stuff, you want to use flow for like high bandwidth, and then you want to use Digicel for something else. You could play with you can actually play with the routers and everything in there, play with the traffic flow, but yeah, it's best to use a proper firewall to do it because it'll do the work for you. Right. So as I say, PC1 sends a data link PDU frame across the medium to the router, right? So remember I said it has to do a frame, but it has the destination MAC, which is the router destination MAC. It'll learn that through the app and it'll build the frame out, right? It contains the IP packet, yes. And it also contains the source destination MAC, source destination IP address as well in that frame. So we move it on. So the router has received this. So this will be in router 1 and router 2. Both steps, we cannot follow them one after the other. Right, so each router, and this is like when you start it up and everything, it keeps an IP router table in memory or in its RAM. You guys could read up more about the lab 1 content talks about router, RAM, and all these things. So you guys could read it up. Those things will come in multiple choice and stuff. So you guys have to read that up, right? But the concept is because what's about RAM and VRAM and stuff. You'll read about NVRAM in the slides, right? But I'll just give you a summary of it. You know about RAM, right? You guys know about RAM. Good. So basically, that's very fast memory. If you pull power on it, it will you'll lose that information. Some systems do have a battery to keep it running, but that's more specialized systems. That's RAM. Same thing. What happens to the router? You pull power on a router, whatever in RAM is gone. Plug back any power, and it starts back up. It has to reload stuff into RAM, including the IP routing table. So the interesting thing about IP routing table is that it has certain processes how it builds this routing table. What happens? In this case, when we go into later on with more routing, we will discuss how this table is built up. And in addition to that, well, why this table looks like that. And when we go dynamic routing protocols, you're going to see how that is going to build that routing table too. Right? But the routing table, once there's a routing table, the router can do the work. If this routing table is empty, then the router cannot do any traffic routing. It cannot do job. As what they say, you have one job to do, and the routing table is empty. You just had one job, and well, you're just sitting down there doing nothing at this point. Right? So that's what routing table is very important. So it lists IP groupings, IP networks and subnets, which we'll deal with later on. And what's happening is that all packets that enters the routers, so what it's looking at is the destination IP address, right, will be compared to the entries in the routing table, and it'll do bitwise matching. So it's just going to convert it into, it's going to take it, I think, let me see. It's going to take the IP, I think it's, yeah, the destination IP is going to take that, take the routing entries. Remember, the routing entries have prefixes in that. So it's actually going to use a bitwise matching between the destination IP, the routing table entry, and their own mask. And they're going to do bitwise matching. And if it's the same, it's going to say, okay, this network, or what I'm seeing here, that's where that destination belongs in that network. And then it's going to find out where to send it after that. The router will do that, right? So it has to do, it does an bitwise matching. Now, there's a little more caveat, a little more steps to that bitwise matching, because you can actually have what you call longer bit matching. The longer the bit matching that is valid, the better the more preferred route to take. So you could say, okay, one route could take you all the way somewhere, and then the other one could take you directly connected. And that's actually a better bitwise matching, and it's right there. And well, that's the logic behind it. The better the bitwise matching is, the better the chance it might be closer to the router, as opposed to going all the way out to the internet, coming back in. So that's one thing with bitwise matching. We'll deal with that later on when we actually show routing flows. Right, compare the entry routing table. In this case, right, so we're doing both. R1 and R2 will have matched the destination address. Now, we are not seeing the routing table, but we'll see that in some of the slides. Will show you what it looks like. When I do the labs, we can actually do show IP route, and you'll see what the routing table looks like. Right, we'll have matched destination address. This is 192.168.111. Now, you'll notice a few things. They don't have it here. But all these routers, most of them do not have this IP address, the destination IP. That destination IP is all the way on the other side. But everybody else in between is have like 150 or something else on the internet, or 10 or something. So you want to know, well, how is that related? Those are just communicate one another. That's how it's set up. This is being encapsulated. The 192.168 packet is being encapsulated, and that's being sent across. So it's going to match. It tells R1, in this case, it tells R1 to send the packet to R2 next. In this case, it's going through this link on the left-hand side. So it's going to go through this link on the left-hand side, and this is R2 on that side. That's where it's going to go. So let me just run an next arrow here, going across here. Right? It's going to send it to R2, the R2 router, and it's going to do the same operation. It's going to take that packet, match it with its own router table, which could be different. In most cases, should be different. And then tell you, hey, it's going to be in a different, going to go somewhere else. And in this case, it's going to send it out through another interface down there. And it's going to go something called EO-MPLS, Ethernet over MPLS. Right, that's a WAN protocol. So you'll notice a few things. One thing, something called serial first, and then something called EO-MPLS. Right, so this is actually demonstrating that the packet can actually go through different types of networks. Not just LAN networks that we are doing in this course, but WAN networks as well. Because IP is basically is routable. That could go anywhere, anywhere. You could see it from the internet. You could see it from home. Right. When we go into more details, you have to public and private IPs, which I think I might be able to. I might or might not be able to address that today. Yeah. MPLS, right? MPLS is multi-packet label switching. It's a older technology. The newer one is like Metro E is the better one. E is Ethernet. So it's basically running the Ethernet protocol over MPLS, which is cool. This was what I love about something called, and once you get the terminology of encapsulation, you can encapsulate other network protocols inside of other network protocols. So in this case, it's Ethernet encapsulated MPLS. So you have a whole MPLS network, which is what the ISPs will use, TSCT, especially TSCT and stuff. They will have that all over the country. And they could then encapsulate Ethernet over it. So then you could literally take a cable from your laptop here, plug into the correct device, and then you actually can see if it's done well, you can actually just do a broadcast and see another device on the other side of the network, which could be halfway through on the other side of the country, and they appear to be on the same network in terms of broadcasts. It can be done. Normally, you don't really do that in that level. Now, just to digress a bit, you can do Ethernet over IP. So I just realized I just told you something different too now, right? So you have EO MPLS. You could also do EO IP. So you could take a layer 2 protocol, encapsulate that, and put it on top of a layer 3 protocol IP and send that across. Now, I don't think you guys will understand how great that is and how good and bad that is. But Ethernet over IP means that I can actually have my laptop set up, go through a device, which is Ethernet over IP, connect to another device across the country or internet around the world. And all it has to do is just do a broadcast, just an IP broadcast, and it'll see the other devices if it's on the same network. Right? It's seeing it on the same network. You're thinking, hey, I could just ping on just one single IP, like you're 192.168.1.1.1, while the other one is 1.1.1.2. And that is where Ethernet over IP will help with that one. To set it up is some tunneling and stuff you have to do. But a device that does that is something called MikroTik. Let's write that down so you guys could the equipment is some equipment, not too costly. MICROTIK, I think. You guys could check it out. Right, so I'm just gonna put EOIP. Right, you guys could check it out. They have some software and stuff. This is good. I have not set it up yet, but it's something that I would like to do. I think these guys, Seismic Survey, they use MikroTik for their stuff. They use it because they have to do packet radio between the different islands. So they actually have satellite, or not satellite, packet radio. So they're using like long range radio between different islands, and they then use that. They send data over that radio link, and then they use MikroTik to then convert that to IP and stuff. So they actually is low bandwidth because it's kind of like low frequency and stuff for the range, so it's low bandwidth. And that's why they could only send out like a few bytes per second or something like that. But that's enough, because that's enough earthquake data and warning sensors and stuff. That's all they need. So that's why they see when they pass there, you see some dishes and stuff. Well, I think it's deprecated, but they have other dishes where that is to send to their other islands, St. Vincent and Martinique, all these guys who have it. Right? So that's not using satellite. That's their own localized from radio to radio, which is good. Perfect for disaster and stuff, which is what is happening. Right, so it's going to R2. R2 is going through this. Yeah, I digressed in a bit, but I'm just telling all these some technologies and explaining them there so that you could see that even though you're going through this, you're seeing different technologies. So when you're setting up something, you know, okay, I am not using MPLS. I'm using just LAN, Ethernet, which is what we will do in this course. You hardly touch these what you call WAN technologies. The WAN course will deal with those. Right, since R3 will then take that information and repeat it again. Same logic, so you realize ladder, rinse, repeat kind of thing. You're going to take this information, compare it, and then send it out. Now, you may say, okay, well, at what end is when it's going to stop? Right? So there are more steps, again, in the underlying process. These online steps, as you guys know, other than the matching, is, you know, about the encapsulation and decapsulation of the frames and stuff, right? Where they encapsulate layer 1 to layer 2 to layer 3, and then decapsulate back to layer 2 to layer 1, send it out the line, and then come back up. Right? So each time it hits a router, it actually encapsulates and sends it down the line. When it goes to the other router, it then takes that information, decapsulates it, processes it, and then matches, and then send it, re-encapsulate and send it back down. So it actually goes up the IP stack or the TCP stack, and then go back down. Now, different devices will determine how high it goes up the stack. Switches will go up to layer 2 because it just frame forwarded. Routers go up to layer 3 because it has to analyze the contents of the packet to know destination, source, destination IP. And firewalls and stuff, they go up to layer 4 and layer 7 because of application. Needs to know what it is running there. SSL and all these guys. Right, so that's the underlying process that we're talking about. Then PC2 receives the packet because its IP address matches the destination IP address in the packet. it matches me because of that. Not just the MAC address it matches, but it's the packet address to me. Then I will be able to process it, and I'll then do whatever I want to do with the data. Right? Now, there are cases where you have Wireshark or in this guy, and the time answer anything coming to him, you set it to accept everything. What you do with it, well, then that's where your Wireshark data capture will show you what's coming inside. Right? So that's essentially how this routing will work with this step. Let me do a simple trace route, because you'll want to know I really hope it helps with. Guys, can tell me which one of these are private IPs and which are public IPs? You see this, right? Zoom in. Which is private, which is public? Right, this one is private. Right, the second one is private. This third one here. That's this private, public. That's public. This one, public. 10.2.2.3 is public. Verify that one, right? Anything 10 is supposed to be private. So I wouldn't know how that public, but there's a website called ipinfo.io. You could check that out. I use that with the WAN course. Right? So some of you want to know, hey, why am I doing this? This google.com, this is like really lovely. Right, okay, that's perfect. Okay. Every one of these IPs here is a router. It's an interface to a router. Now, the thing about it is that this 172.1.18.0.1 will most likely be my default gateway router. And how would I know that? I'll just do here IP config. You do IP config and see what you're getting, right? 172.18.0.1 set up by my DHCP server. I'll leave it up to you guys to figure out how big this network is. All right, something to additional info, right? So this is, and what network you're on right now? You have no idea, right? One way to tell is how you investigate this. You go down to your physical layers and you check the right. You just check this. All right, you love Windows, right? Okay. Hope it gets it. No, it's not coming up properly. Oh no, it just swapped. It just thinking. Right. Physical, guys, you have to check your physical layers. So that's Wi-Fi SDA test. So you notice is your Wi-Fi adapter. Sometimes you may have a Wi-Fi 2, Wi-Fi 3, because those who like to have multiple USB NICs, USB and Wi-Fi NIC dongles, you've got 2 and 3. And then you know the SSID connected to. So SDA tests, for sure, this is going to be connected to UWI Campus wireless network. That's one. And I'm streaming through that. So hopefully the stream will be good. That's 1. 2. Look at it. My IPv4 address is down here. And 172.18.0.1 is the default gateway. So this is from the Windows interface. I'm getting this info. What about that? So now, okay, I established, okay, based on how it is my physical device is connected to this. That is the data I have there. Use a screenshot, keep that in our record somewhere. Close that down. Come back, matching it back up. IP config. So yes, this is matching up to what is showing in the windows, great. So then I can start to work in my command prompt. Now I verify. So now I can work in my command prompt and then work from there. 172.18.0.1, let's go back up to our trace route. There it is. So this guy, first hop, is their default gateway, which means that all of these, right? So let me just go back. And the reason why I'm doing this, because this is kind of going to help when you're going to do later on in the Modi group project. It was also a problem for the WAN course too, because they had to do a trace route for maybe about double this length of routes, and they had to build out the network. And it was much more work. So they have to understand well how to set up the IP addresses on the interfaces. So what happens is that this router will have an interface that is facing my end, that is this value. The second router will have an interface of this facing the first one, but let me show you how that will work. You just resize this properly. Right, I think this might help. Up there. Good. Right? 172.18.0.1 would be this one, this R2. That's that interface above R2. In this scenario, if my PC was directly connected, as wireless, that's what this interface is. Right? 10.0.0.2 is going to be an interface on this side. Right? That's where 10.0.0.2 will be if you're building it out. Which means if 10.0.0.2 is here, they need to be on the other interface on this side, what the IP will be. It might be 10.0.0.1. Right, so it might be 10.0.0.1. You ask, well, why is it 10.0.0.1? It's going to be, if it's /24, it will be on the same subnet. Right, that's why you have to know about IP subnetting as well, to know that, hey, how come I get a 10.0.0.1? It could be 10.0.0.4 as well. It'll work once it's in the same subnet if it's a /24. And that's why you have to know IP subnetting. If it's a /24, a /22, or even a /26 or 27. Because when you start to use that, that is going to determine if they're going to be in the same network or broadcast domain as they call it. When we start to do VLANs, you're going to see funny things happening there with VLANs. Because VLANs is logically separate networks. And but you're going to have multiple broadcast domains in a single VLAN. And I will demonstrate that. I think one of the labs will demonstrate that. Really interesting. But it's, I guess, got that concept in there as well. So that's good. This guy, 64, 28, 140, 61, will be on the interface on the next router going on the line. Well, of course, it's the PC here. But in that case, that's what this guy would be. 64.140.61. That's what this PC would be. Therefore, the interface here would be something like 140.1 or something of thereabouts. Now, our configuration in network here, chances are this is a firewall device, a specialized firewall device this is hitting up at. So it's not really a router on the internet, it's a firewall device. And that's why this is a 10.2 as well. So it's kind of complicated. So it kind of hits a public IP, which is actually publicly on the campus, but it's not, you can't really see this IP per se. And then it hits the internal, almost like this internal firewall, and then it starts to go out here. This will be, if you do this IP info, this will most likely be attached to flow. So you can actually identify who's the ISP that owns this IP block. This IP block here is owned by UE, so you see UE owns this IP block. Right? It's owned, it is because this is registered with INE and then BGP routing and all those things. That's why you can see it. Right? And then you can do your research and find out who owns all these IPs later on. But the reason why I'm going through this detail is because I want to show you how this routing, how this trace route is, and how it looks like when you're doing this routing. So you get a trace route, and then from there, when you get anybody who does a trace route now, let's say, okay, this is a router, that's a router, that's a router, that's a router. And then when you can actually create back out and how the assimilated network, what it might look like. All right, so that's what group project for the WAN course did that. LAN course, not as much detail. You guys will get something smaller because you're more focused on the LAN. right? So I'll skip this. This is things like same layer interaction and adjacent layer interaction, right? So you have an idea what same layer interaction is, layer tree to layer tree. And how layer tree to layer tree works is basically IP source destination to IP source destination. As how they work. That's the logic between the two different, and these are different devices in most cases. Might be the same one if it encapsulates and decapsulates. But if it's dealing with multiple other devices, that's same layer. So that all it is doing is find out who's the destination and send it out the other side. Same thing with frames. Frames, same layer interaction. Most cases, it's end up working at more the switch level and not really switch on the other side because that's just localized to the switch. Incoming and outgoing, that's it. That's same layer in that way. But if you want to go same layer, like multiple devices, the only way is to go up the layers because that's when things like layer 4 comes in TCP. TCP deals with segments, it deals with you arrange your data into different segments and then it had to reassemble. Right, that's same layer happening with TCP because the device on the other side now have to take all the TCP segments and reassemble. That same layer at TCP level, right? It's not really worrying about it below, it's just waiting for those things to come to it and then it works at same layer TCP to assemble. Same thing with your firewalls and the application, which is HTTP or FTP and all those things. Same thing, right? That's the same layer. And adjacent layer is more the easier one, that's it going up and down the TCP stack. So anything that is adjacent is basically like from physical layer, data link layer. You're going up to the IP layer, then you have the layer 4, which is either TCP, UDP, and then you keep going. So as it's going up the stack, that's basically adjacent because the word adjacent are not one another, they're not on the same number. So same layer, just look at this, the same number or protocol data unit level, or same layer, same level. Right, that's same layer. So it's the same number and you work with that. Adjacent means that it's going up and down the stack. So this the one next to one another on the same device. Right, so we just talk about encapsulation, decapsulation, and handoff. So you guys know about this a bit. Right, so this little summary here. What it's saying here, routing, the IP addresses are preserved. So once it's an IP packet, the data is, the contents are preserved. They're not going to modify it or destroy it. So, and that's the thing about IP. Even with our network here, if I put a packet here, the ping packet I sent to Google, that packet is essentially the same. I mean, the electrical signal is recreated each time, but the actual contents of the packet is the same from here all the way to Google. And when Google responds, it creates a response packet, not my same packet. It takes a response packet, send it back to me. Right, but that packet coming back to me, that data source that is preserved. So it's nothing it's not destroyed in this case. In our case of UE and firewalls, the data is remapped. Some things are remapped. So some things are destroyed because if Google does a search to find out who am I, they would not find my 172 IP because that's a private IP. All it's really seen is the 64 IP, which is the public facing. When you do the WAN course, you'll talk about network address translation and port address translations and firewalls and stuff like that, where it actually takes your IP and map it to a public IP and port mapping, and then sends that out. That's when you do a what is my IP, that's what it's seeing, is whatever outline facing. So those who have firewalls and stuff, it would, that's where you have to kind of understand how mapping works with that. But anyhow, so these are preserved. Anything, just get this, everything below layer 3 are deconstructed and then reconstructed re-encapsulation. So anything below that, so your frames that are, so remember when you're going down the stack, it keeps adding on more and more headers and trails to the device, and it keeps going down. So it's adding, when it's going to frame level, it's going to add the header, the frame headers and stuff, and the checksum. And then when it goes down to the electrical signals, the binary bits and bytes and the signals, it's going to send that across the link. The device on the other side is going to receive that. When it takes to the frame level, it's going to strip out those frames because that's basically localized between the immediate devices. And then it's going to make a decision who to send it next. And then it's going to re-encapsulate with a new frame header and trailer, but the IP itself destination remains the same. Right? So that's what it's saying here. Of course, you have cases of the ARP, and I mentioned ARP and all these things before, how they knew it, right? So I talked about that before. and then we explain it here again. Right. So they mentioned something about LANs and WANs. So as I said, we don't have to worry much about WANs and WAN protocols. You could consider WAN operating like a regular layer 2. All these are kind of like layer 2 stuff. And it's just a matter of the right, I guess the best analogy would be, best way to, how did we do that? Convert it. I think the best analogy is like, say, a video file, for instance, where your phone could actually save a video to a certain format. Or, iPhone does a new HEV format. I don't know what to call it. So the iPhone can save it, but Windows cannot read it. So you'll have to go to a device that can actually understand both. So yeah, most likely somebody, Mac or something, will take that. You'll take the Mac, open up the file, HEV file, and then convert it to either MP4 or MKV or something like that. And that's what happens. So what's happening here is that you go to a device that has both. So in this case, this guy has a serial and he has Ethernet. So because he has both the hardware devices connected, it should be able to translate from the data from the Ethernet side to something on the serial link side. It's going to actually convert that. Now, you ask yourself, okay, well, what about the IP packet? IP packet is preserved. That is layer 3 stuff. That's going right across. It's not IC. It's the layer 2 stuff is where it's deconstructed, and that's what's going to happen here. It's going to destroy the Ethernet frame at this point here. The Ethernet frame is destroyed, and it's going to recreate something called a HDLC frame here. Different layer 2 protocol. And recreate that frame, and it's going to go to the other device, R2. R2 is going to take that, then destroy the HDLC, and then put it into MPLS, EU MPLS frame, and then send it across to R3, and then it's going to repeat that process, right? So the devices know how to take, because they have the interfaces. Now, the iOS, all that thing will deal with that once you have the right hardware. Right, it'll do that. Right? Right, IP addressing, how it helps IP routing. As I mentioned, yes, a group of IP addresses. This is going to go, let me just skip through this. You guys know about, I want to finish this off fast. More or less have to finish. Right? Don't need to worry too much about, I'll tell you what you need to worry about. This piece here is what you really need to worry about in this IP, this 4-byte IP address layout. Most of this itself is preserved. Let me tell you what's happening here. It will put this is the IPv4 header. When it goes from your PC out there to Google, this is going to stay. In most cases, this will not change. What's going to happen is that the frame, I'll go put that in. Frame check sequence, FCS, sorry. Frame header. So what's happening is the router is actually going to put on a frame header and check sequence at the end, encapsulate IP, and send it across. So the source destination IP addresses, that's not going to change. The content time to live, the time to live does change as you do if you do a ping operation. Each time you do a hop, the time to live value is decremented, so it reduces. Protocol remains the same because it's IP protocol and the type. The checksum for the IP is the same, and that doesn't change because the data content doesn't change. You have different things, packet and stuff should not change. Right, so that's the case of the IPv4. The packet. Let me see how fast. Guess you guys could read up the rest. All right, let me skip this thing. Routing protocol. Let me know if you have any questions on these things. Right, routing protocols. So first things first. The routing table is a source of truth for an IP packet to determine where it ultimately goes. So the routing table, and as I mentioned before, as I said, I'll come to it, that contains where the packet will go, or where the router will take, or how it will deal with this packet when it gets it. Like I said, if that routing table is empty, like the router had one job to do, the routing table is empty, it's not going to do anything. So the thing is, how do we get this routing table created? And you have different mechanisms. So how would you get it? So we could create the ID manually by the administrator. You could use up the routing protocols to create a table, which is what we'll do later. And we do all of this. And what I'm missing here is that when you as routing protocols, when you configure an IP address on a routing interface, that is added onto the routing table. Once it's what they call an active state, the interface is up and running, and you will see it in the lab. Once it sits there, that is where the routing table will be populated with that information. And you ask yourself, why? Because it has an IP. That means a network exists. And that's why it added to the routing table. You can override and say, no, that's not the case. But by default, that's what's going to happen. It's going to be there because it's configured and it's active. It's supposed to be. That's how it naturally works. Everything else is done manually or by other protocols. But this is one thing. The moment you set an IP and it's active interface, it's going to go on the routing table. So that's the first thing that's going to happen. Everything else is done afterwards, either by yourself or the protocols. Right? Routing protocols, we'll talk about that later. When I start to route protocols, if you guys want me to go through this, let me know. I could go through this because I need to push ahead into IPv6 more or less next week. Right? Host routing, we could skip this. I think you have an idea. We did all of this already. They put an example of the next hop IPs in this in more detail. So you guys could just take this, what I did early on, and then match it back to this. This would be the same thing, right? Now we're adding IP addresses as the next hop IP. And then look at this. They demonstrated what a sample routing table look like. Now, it's not the exact same thing. You could do an IP. Let me see if I could do it. Did I clear it? Will it work? Yep, that's it. Guess what, guys? Yes, my PC does have a routing table. Makes sense? We'll check it out later when you're ready, right? Yeah, all this is, yeah, you want to know what all this about, right? So this is actually a route IPv4 routing table on this my PC. So your PC itself has a routing table in addition to your default gateway. So you can actually add some additional stuff here. All this is because of virtual interfaces and stuff I have, because of VirtualBox, VMware, and all this dependent, right? They have some broadcast stuff here and some other broadcast stuff here. We're not worrying about that. And look, this is the persistent one. What is that doing there? 1.1. All right, I don't know how this got there. That's supposed to have wireless. I don't know how this is. All right, and this IPv6 routing table. Right, okay, that's it. This is it. I'll discuss later how this works, matching all these zeros and stuff, because this is what we're using right now. Right? So I'll wrap it up today. Just showing you how easy it is to start to get into your routing table and literally on your PC. You even have to touch Cisco Packet Tracer or even GNS3. All right, guys. So I will see you on this Saturday labs hybrid. As this lab will be hybrid, so you guys who can't make it could check online. It's going to be recorded just like what I'm doing today. So I'll post those recordings online. Labs are important. So, all right. So don't forget attendance. Please fill out your attendance sheet. Pass it on. Just sign on it. Thanks. All right. So I'll end off the Zoom session. And I'll see you guys on Saturday. Yep, later.
You'll be teaching us how to use GNS3 and all that? Or should we come knowing how it will operate?
You will have to learn the GNS3 anyway. I had videos on how to set it up. So
Yeah, that is a
you set up right. So that's basically you're starting with that, and then from there you're gonna learn how to do certain things.
okay. No.
I might all right, okay. I might do a demo. If you need to, I might do a demo in the lab or something at some point. But
It's similar to Cisco.
the commands and stuff it is Cisco commands.
Okay.
It is. That's why I want to use GNS3. Remember, that's just assignment group project. Packet tracer is what will be used in the labs.
Okay.
And people ask, well, why both? Because packet tracer is set up because the lab exam is packet tracer. And the group project is GNS3 because you have more time, you can take it home and you could use the setup like that. And you get experience with the platforms. I really want to do, not this semester, I don't know when I'll get a chance to build out something where you use like Huawei or something, routing or something, because they have their SNMP simulators. But that might be a more difficult. It's not as easy as packages. It's more complicated. So that why I do like to use the Huawei. All right. Any other questions? Are you good?
Yeah.
All right.
So the lab is physical stuff.
It's in person, but it's hybrid.
So I could okay.
Yeah, I know everybody wants to go and say, well, no, attend the lab.